To show that this vector A, which is -9, -7, -15, is a linear combination of vectors u, v, and w, we need to establish or to show there are certain k scalars, since we have three vectors here, k sub 1, k sub 2, and k sub 3. We will need to show that k sub 1, k sub 2, and k sub 3, all of them are scalars, exist. If we cannot show that they exist, then the vector -9, -7, -15 is not a linear combination of vectors u, v, and w. And we can show the presence or absence of k sub 1, k sub 2, k sub 3 when we show it like this. You have -9, -7, -15 must be equal to k sub 1 times u plus k sub 2 times v plus k sub 3 times w. Okay, so we'll have -9, -7, -15 here is equal to k sub 1 times your u, which is 2, 1, and 4, plus k sub 2, your vector v is 1, -1, and 3, plus k sub 3, which is 3, 2, and 5. Since we, what do you call this one? We consider that k sub 1, k sub 2, and k sub 3 are all scalars, so we can use scalar multiplication to these three sets here. So this is still -9, -7, -15 is equal to 2 k sub 1, you will have k sub 1, and 4 k sub 1, plus k sub 2, negative k sub 2, and 3 k sub 2, plus 3 k sub 3, 2 k sub 3, and 5 k sub 3. Now that we have this, we can use the vector addition here. -9, -7, -15 here still. You will have 2 k sub 1 plus k sub 2, all the first entries, plus 3 k sub 3. Then this is, the next one is k sub 1 minus k sub 2 plus 2 k sub 3. Then you will have 4 k sub 1 plus 3 k sub 2 and plus 5 k sub 3. For equality of vectors now, we could come up with this system where we equate this by this value and so on and so forth. 2k sub 1 plus k sub 2 plus 3k sub 3 equal to -9. Next, you have k sub 1 minus k sub 2 plus 2k sub 3 is equal to -7. And 4 k sub 1 plus 3 k sub 2 plus 5 k sub 3 is equal to -15. We have a system here, and since our goal is to show whether k sub 1, k sub 2, and k sub 3 exist, we need to show if they have if this system has a solution. So to do that, let's have this augmented matrix here, 2, 1, 3 for all the coefficients of the first row together with its constant here. So you have 1, -1, 2, -7, 4, 3, 5, and -15. So we are going to show or use the Gauss-Jordan elimination, or in short, try to come up with this, the equivalent of the reduced row echelon of this, to see if we could show exact value for k sub 1, k sub 2, k sub 3, and if they exist, or if they do exist, and we could decide that originally the vector -9, -7, -15 is a linear combination of vectors u, v, and w. So let's start. Would like to interchange row 1 and row 2 so that I will have leading 1 on my first row, 1, -1, 2, -7. So I have 2, 1, 3, -9, 4, 3, 5, negative 15. And I'm going to apply elementary row operations here. So it will take long, but this is the process for verification here. So I would like to multiply negative 2 to row 1, add it to row 2 for a new row 2, and multiply negative 4 to row 1, add it to row 3 to have a new row 3. So we have 1, negative 1, 2, negative 7. So negative 2 times 1 is negative 2 plus 2, 0. Negative 2 times negative 1 is positive 2 plus 1, 3. Negative 2 times 2 is negative 4 plus 3, negative 1. Negative 2 times negative 7 is positive 14 plus negative 9 is I have here 5. Let me check. 7 times 2, 14. Then you have negative 9. That's 5. That's correct. Then we have for the third row, negative 4 times 1 is negative 4 plus 4, 0. See, we have here other 0 entries below the leading one. Next, negative 4 times 1 is positive 4 plus 3, 7. Negative 4 times 2 is negative 8 plus 5 is negative 3. Negative 4 times negative 2 is 28 plus negative 15 is 13. Here next, we are going to, let's try to divide or multiply row 2 by 1/3 for a new row 2 before application of the next row operations. 1, negative 1, 2, negative 7, so 0. This is now 1. This is negative 1/3. This is now 5/3. 0, 7, negative 3, and 13. And I'm going to multiply negative 7 to row 2 plus row 3 for a new row 3 to make this 0. So I have here, I don't know if I still have a lot of space. I will be using some of the space here on the left hand side, or right hand side rather, but let me just continue this one here. 1, negative 1, 2, negative 7, 0, 1, negative 1/3, 5/3. 0, negative 7 times 1 is negative 7 plus 7, 0. Negative 7 times negative 1/3 is 7/3. Negative 3 is negative 9/3, so this is negative 2/3 here. Negative 7 times 5 is negative 35/3, and 13 here is positive 39/3. Negative 35, positive 39, so you have positive 4/3. Let me check. Negative 35, and then you have your 39, so that's it. Now I'm going to multiply negative 3/2 to our row 3 for our new row 3. And I have here still 1, negative 1, 2, negative 7, 0, 1, negative 1/3, 5/3, 0, 0, this is now 1, and since we have 4/3 times negative 3/2, so that's 2, but more specifically negative 2. Now we have already the result here, and we can just simply use that to solve for the next, but since I do have fractions here, I'm just going to continue and now make target this to become 0 and this later as well. Let's start first by multiplying 1/3 to our row 3 and add it to row 2 for a new row 2, and multiplying negative 2 to row 3 plus row 1 to have a new row 1. So again, let me use some spaces here. So this would be still 1, negative 1, 2, negative 7 here. Sorry, I'll be changing some of the entries for row 1. So I'm going to start with row 3, 0, 0, 1, negative 2. This is still 0. So for row 2, 1/3 times 0, this is still 1, right? 1/3 times 1 is positive 1/3 times 1/3, negative 1/3, plus negative 1/3, that's 0. So 1/3 times this is negative 2/3, 5/3, that's 3/3, I have 1. Okay, that's for the second row. For the first row, negative 2, okay? Negative 2, so this will still be negative 1 because the multiplier here is 0. But for the third column, negative 2 times 1 is negative 2 plus 2, 0. And for the other side, negative 2 times negative 2 is positive 4 plus negative 7, negative 3. So we still have one more step. One more step here is if we are going to add row 2 and row 1 for a new row 1 to make this 0. Okay? So our final form, and this is now our reduced row echelon form, 0, 0, 1, negative 2 for the third row. We also did not alter anything for a second row. And we will add 0 plus 1, 1. 1 plus negative 1, 0. 0 plus 0, 0. 1 plus negative 3 is negative 2. This is already our reduced row echelon form. And this means that our first coefficient, which is actually earlier k sub 1, then k sub 2, k sub 3 here, that pattern. We can now say that k sub 1 is equal to negative 2, k sub 2 is 1, and k sub 3 is negative 2. Since both are all, not just both, all these three coefficients exist, this means that our original, vector here, negative 9, negative 7, negative 5, is a linear combination. This is a big yes. Linear combination of vectors u, v, and w, because again, k sub 1, k sub 2, and k sub 3 exist as scalar. Thank you for watching.